Hey everybody, Mr. Alsop here coming to you again from my amazing living room studio. Today we're going to jump right into things because we are talking about a very important scientific subject. A scientific subject that will be with you whether you're doing biology or chemistry, whether you're talking about physics or earth science. It cuts across all of them, and it's an integral part of what we need to do science in middle school and in high school. So we're going to take a look today at a concept called density. And in order to discuss density, we're going to have to cut through a bunch of other topics because everything that goes into density we need to understand before we can really understand what density is and how it works. So the main question that we're trying to answer today is what are some reasons that things might float or might sink? So we all know that when we drop something into a body of water, whether it's a bathtub or a lake or an ocean, that there are different reactions that can happen. Sometimes when you throw something into a body of water, it floats up to the surface. Sometimes it sinks down to the bottom. Sometimes that sinking takes longer, and sometimes that floating isn't always complete. Sometimes stuff sits in the water and is partway into the water and partway out of the water. And sometimes it's almost all the way out of the water, and sometimes it's hanging down so that almost all of it is in the water and it's just barely floating at the top. All of those are interesting phenomena. And they all show us that there's more to this idea of floating and sinking than just a simple, oh, it either sinks or it floats, because there's degrees of sinking and floating. Now, in order to really understand this, there's a scientific concept that we have to think about called mass. Now, mass is the amount of stuff that's in an object. And I know that a lot of times your science teachers are going to tell you that stuff is not a very scientific word. But in this case, I think it's one of the better words that we can use here, because that stuff that's in an object, we don't always want to quantify what we mean when we say stuff. Generally, when we're talking about this, though, what we are thinking about is, think about, for example, an elephant. And when we have an elephant there, we think about how much stuff is in that elephant. And there's a lot of stuff inside of an elephant. So an elephant probably has quite a bit of mass. On the other hand, a basketball, which is much smaller, might not have as much stuff in it. So it might not have as much mass as an elephant. So that's our first concept, is thinking about mass, the amount of stuff that's in an object. Now, what kind of stuff might be in there? Well, in order to understand this, we have to kind of think about atoms. Now, atoms are the building blocks of everything. So everything is made out of atoms. Now, you've probably heard your science teachers talking about cells and how cells are the building blocks of all living things, and that is true. And atoms make up cells. So cells are made out of atoms, so atoms are the building blocks of those cells. But atoms aren't just the building blocks of living things like cells are. Atoms are the building blocks of everything, even things that aren't alive. Things like certain kinds of rocks that have never been alive and are not alive now. Those kinds of things are still built out of atoms. So atoms are these building blocks of everything. But the other key part of it is atoms have to still be that thing. So if you have an atom of gold is still gold. If you break that atom down farther into its protons, its neutrons, and its electrons, those protons, neutrons, and electrons are no longer specifically gold protons or gold neutrons or gold electrons, the way a gold atom is still a gold atom. So there's a difference there in how those building blocks are oriented, because an atom is still the thing. An atom is still gold. But when you go below that, it's no longer that thing anymore. It's no longer gold anymore. And when we say that thing, what we're really talking about here are those elements from the periodic table of the elements. Now, the cool thing is that not every atom is the same. Just like not every person is the same, just like not every dog is the same, just like not every cloud is the same, not every atom is the same. They all have the same basic structure. They all have some things in common, so they're not all completely different from each other, but they're different enough that they can create different, what we call elements, different things that exist in our universe. And so we talked about gold. On the right-hand side of the screen here is an atom called carbon. And carbon is one of those atoms that generally we think about making up us, people and other living things. Carbon is kind of one of those backbone atoms of living things. And on the other side, we have oxygen. And oxygen is another type of atom. And oxygen is a gas that's in the air that when we breathe it in, we actually use oxygen from our air to help us break down other molecules into energy for our body. So these two atoms are both found in us, but they're not the same. And this is kind of a way of visualizing atoms. This is called a ring model of an atom. In the center of this ring model is the nucleus of the atom, where the protons and the neutrons are. And around it are rings of what we call electrons. And we can see in this case, the electron rings have different numbers of electrons in it. In the nucleus of the atom, there are different numbers of protons and different numbers of neutrons. And that's what helps to make each atom different from each other, is those numbers of things that are in the atoms. So when we think about these atoms, not every atom is the same. They all have a little bit of a difference for different elements, for different things. And so when we're thinking about something like mass of an object, we're thinking about maybe how many atoms are in the object. We're not so concerned with what kinds of atoms they are necessarily. We just want to know how many atoms are in there. Now, those differences among those atoms make the atoms what they are. We talked about how one atom has more protons, more neutrons, more electrons. It's going to be a different element than some other atom that maybe has fewer protons, fewer neutrons, fewer electrons. I like to think of it in terms of animals. You know, if I look at, for example, a spider and a tick, they both have 8 legs. Okay, neither of them have any antenna. They have a lot in common, but there's some significant differences between them. And it's the same way with atoms. Atoms of different materials have a lot of things in common. They all have a nucleus, they all have electrons, but they might have different numbers of things. They might have different kinds of things going on them. And it's important to remember that differences are out there. Differences are in nature, and differences are all over the place. And if it wasn't for differences in things, we wouldn't have the world that we had. Now, some scientists, when you ask them, you say, well, so if the mass of something is how many atoms are in it, basically, how much stuff is in there, how many of those little component parts of atoms are in there, how many neutrons, how many protons, how many electrons, if we took all of that stuff and added it all up, what would we get? How do we measure that? Because I can't see an atom, and I don't know how to weigh an atom, and I don't know how to measure an atom. I don't know how to measure how many of those there are. How do we do this? And the simple answer is we can weigh the object. Now, the mass of an object is equal to its weight here on Earth. So if we have an object, we can put it onto something like a triple beam balance, like on the left. Triple beam balances, you'll find them in all sorts of science classrooms. And they're designed to weigh things in a science classroom so we can determine how much something weighs. On the right-hand side is what we call a laboratory scale. It's a scale inside of a little box, and it's in that little box so that nothing from outside of the box influences the weight of the thing that's inside of the box. And so we could weigh something on that and find out a little bit more about how much it weighs. And when we weigh something, the end result of weighing it is we find out the mass of that object. Now, some of you are probably wondering, well, wait a minute. There's something else there besides just weight. You were very specific and you said the weight on Earth. Why did you say on Earth? And the reason for that is that weight can change when you go different places in the universe. If you go from Earth and go to the moon, an object that had a weight here on Earth, when you go to the moon and you try to weigh that object, it will weigh less. If you bring that same object to Mars, it will weigh less on Mars than it did on Earth. And that's simply because of how the effects of gravity work. So, because we live here on Earth, when we started to figure out how much things weighed and how that related to their mass, we decided that it would be a really good idea to make mass equal to weight here on Earth. Now, the cool thing is, as we go through the universe and as we go to all these different places and the weight changes depending on where we go, the mass of an object always stays the same. So wherever we go in the universe, the object has the same mass, which is its weight here on Earth. But depending on what planet we're on, it may weigh less, but it maintains the same mass. So we have to be very careful. If some of you someday are watching this video and you're on Mars in your Mars colony and you're like, oh, I can compute the density of an object by using its mass, you have to remember to correct for gravity on Mars. That's going to be hard. I really feel sorry for those kids in the future who are going to be living on Mars and are going to have to correct everything for Martian gravity. Oh, it's terrible. So that is an important part of this, though, is that we're here on Earth and we have to think about how this works here on Earth. Okay. Now, remember back to our original question. Our original question here was, what are some reasons that things might float or sink? So, does mass tell us whether or not something floats? Let's think about that. Let's think about some objects with high mass, like, for example, a person. People have a fairly high mass, right? We weigh a decent amount. When we think about our weight and we think about, does that tell us if we float or not? I think the answer is going to surprise you, because generally we think, oh, well, lighter things float and heavier things sink. But that's not always the case. Think about, for example, why Mr. Alsop floats, even though I weigh 200 pounds, but a concrete block that weighs 200 pounds sinks. So there's something else going on here, because it's not completely dependent on the weight of an object. Sometimes an object might actually be much lighter but sink, and an object that's much heavier might float. For example, Mr. Alsop, though he weighs 200 pounds, still floats. But if I throw a little tiny pebble in that doesn't even weigh a pound, it might sink. So there's something else we need to figure out other than just how much something weighs to decide whether or not that something is going to float. And spoiler alert, there's actually more than one thing we would have to figure out. There's actually a couple, 3 different things that might come into it. But today, what we're concerned with is a property of those objects called density. Now, when we think about density, what density does is it compares the mass of an object to the volume of that exact same object. So what we want to think about is, how does the mass of an object compare to the volume of an object? what's volume? How loud it is? Like, we're going to compare the weight of an object to how loud the object is? No. There are different kinds of volume out there. One type of volume that we think about all the time is volume control, like on our iPods and on our laptop computers and all over the place, and on the TV in the living room. We think about the volume. Volume there is referring to changing how loud something is. Volume in science refers to something different. When we talk about volume in science, what we're talking about is how much space something takes up. So in the case of volume in science, the more space something takes up, the more volume it has. So that is going to help us to understand a little bit more about density. If we go back to our last density slide here, and we look at how density is comparing the mass of an object to the volume of that object, now what we're thinking about is how the density of an object is comparing how much it weighs to how much space it takes up. So something that weighs more and takes up less space is different than something that weighs less and takes up more space. Okay? So when we talk about density, what we typically do is we will take the mass of an object and then we will divide it by the volume of the object. Now, the cool thing is that when we do this, we find out that the density of water is exactly 1. And that's one of the things we calibrated our system of measurements on. Now, some of you might be saying, well, wait a minute, what system of measurements are you talking about here? Because there's more than one system of measurements out there. And that is true, in fact. We have the English system of measurements and the metric system of measurements. This works in the metric system. In the English system, you can't necessarily do this with density. Density works in metric. Just like a lot of things in science. Science is very tied in with the metric system. A long time ago, when people were coming up with the metric system, it was mostly scientists that were involved in coming up with the metric system. And when they came up with the system, they decided to make the system work in ways that would help science overall. And so one of the things that they did was they set a density of 1 for water, and then they looked at the mass of water and they tried to figure out how to make that mass over volume equation work such that water would work out to have a density of 1. So this was all done on purpose. It's not just random that water ended up with a density of 1. They wanted water to have a density of 1. Scientists did, to make this easier for everyone. The whole purpose behind the metric system was to make everything easier for everyone. What we call English system of weights and measures was not designed to make things easy for anyone. It was just designed with each individual task in mind, and people set arbitrary figures on things, figures that didn't really mean anything and didn't really have any scientific basis or grounding. And so as a result, that system has not aged well. And so in science, whenever you do anything, you are always, always, always going to use the metric system, because the metric system is generally accepted as the system that scientists would want to use. So this density of water being 1 is not an accident. The other thing that's really cool is that when you look at the density of an object by taking its mass, how much it weighs, and dividing it by its volume, how much space it takes up, what you get is a number. And that number can be less than 1 or greater than 1. If that number is less than 1, then an object floats, kind of like the soccer ball does on the water. If the density of an object is greater than 1, then the object is going to sink, like this golf ball does in water. So when we perform our density equation, what we get is a number. And numbers that are less than 1 in the metric system, as in most systems, we express them in the form of decimals. So they're going to show up as like 0.9, 0.8, 0.7, 0.6, all the way down to 0.1. Those numbers are less than 1. So those objects will float. Numbers above 1, 1.2, 1.3, 1.6, 3, 7, those numbers are greater than 1 and indicate that an object will sink. So when you perform the calculation for density, you can determine whether or not an object floats or sinks relatively easily just based on the number that comes back. The other thing that you can do with that density calculation is you can figure out how close that object is to sinking or floating. So if I have, for example, a beaker over here, and I fill that beaker up with water, so this line here is going to represent that beaker being filled with water, and I take an object, like a little block, and I drop that block into the water, and that block looks like this, okay? Where just about half of that block is going to be above the water line, and just about half that block is going to be below the water line. That means that that block is floating. So if it's floating, based on our last information, we know that it has a density less than water, so it is less than 1. We can look at this and we can actually determine the density of that object by where it floats. Because we know it's less than 1, okay, but we know that it is not fully floating. If it was fully floating, if, for example, I had my block and it was sitting on top of the water like this, okay, that block sitting on top of the water would be very, very close to a density of 0. This block is going to be about halfway between 0 and sinking, which would be 1. So looking at this block, we can determine that the density of this block is going to be somewhere around 0.5, because 0.5 is halfway between 0 and 1. So this density information doesn't just tell us if something sinks or if something floats, but it can also tell us how much something sinks or something floats. So now let's go back and take a look at our beginning picture here. Our beginning picture here shows a battleship. Now, this ship is made out of metal. Metal sinks, doesn't it? So, is the density of the metal keeping this afloat? That's a really interesting question. And I think that's probably going to be our next lesson. What could make this ship float, even though it's made out of a metal whose density would normally sink? There has to be something else going on here. If you were to just measure the volume that that ship takes up, and then measure the weight of that ship, that density of the metal in that ship should indicate that it's going to sink, but it doesn't. Something else is happening here, and that something else is going to be our next lesson. So have a wonderful rest of your week this week, and I'm hoping to see you guys all again on Monday, and we will take a look and investigate how some things that should sink can actually float. See y'all later.